Hello everyone, welcome back to this course on discrete mathematics, and today we are going to look at the applications of relations. And in the previous lectures you have been discussing about relations. There are different types of relations, and specifically we talked about the 6 different ways to express relations. There are even more. We can have various applications that have been derived out of these relations. And in conclusion of the previous lectures, you might be noted that one of the application was about the 6th degree of separation. Well, let's talk about that before we move on to this part 1. Yes, 6th degree of separation. Can you recall what it is? Well, as I told you in the last lecture, this basic idea of 6th degree of separation is like as if any two person in this world are connected by means of 6th degree of separation. As I told you before, like for instance, if suppose consider you and a person somewhere in Africa or Europe or North America, anywhere in the world, even Australia for instance. A person whom you know might know another person who is somewhere else. Say for example you are in Europe and you know someone who is in Eastern Europe, and then that person knows someone in, say for example, in Asia, and this person knows someone in the Eastern Asia, and that person knows someone in Australia, and that person knows someone in, say, Tasmania, the part of Australia. And like any two persons, everybody is connected by means of a 6th degree of separation. And this was in fact proved even before like 1960s. There was an literal experiment was made by means of letter writing back then, and the letter writing process was initiated from one person, and he writes to a person whom he knew, and that person writes a letter to a person whom he knew, and so on, by which everybody else has been connected. It's a random process, but the result proved to be surprising, as it brought out that every person is connected by means of 6th degree of separation. And in the modern world today, we have lots of social networks, and now we can talk about the connections. So yes, the recent articles or research articles on this small world problem indicates that at times even people are separated by means of 6th degree to even 3 degree of separation. Well, in fact, this is where one of the applications of relations comes in. How are they related? How are two persons related? The relation is 6th degree of separation. If you talk about a person whom you know a friend, and that is 1 degree, and then you have another friend, it's like 2 degree. And if you are having an account in either ResearchGate or in LinkedIn, you might see actually what is the link that you have. In fact, that's quite interesting. Well, let's examine more with this of relation. Like for example, R be the relation on the set of all people in the world, and if A comma B, a two person, has the relation R if a person A has met B. The same way it goes on, like B has met C, and C has met D, and D has met E. Finally you have A has met G. So 6th degree of separation for any two person from A to G means that A comma B, B comma C, like A is related to B, B is related to C because they have met each other, and C is related to D, D is related to E, and E is related to F, and F is related to G. Yes, that's where G, we have 6th degree. In fact, I was missing the F when I told you earlier. Here we have the whole stuff. So this degree of separation where A to G, which is an element of this relation R, because we have the degree R, we represent by means of power R, just for the representation. So let's talk about this connectivity problem, the connectivity relationship. And in fact, if you are interested more on this 6 degree of separation as well as the connectivity problem, you can look at a problem called small world problem. And today in a social IoT environment, social Internet of Things environment, we have scrutinized this connectivity problem in a various ways, and nobody knows that like how the problem that was established even before 60 years has been applicable today. Well, let's talk more on this. OR contains edge between all nodes reachable via one edge. Say for example, OR that is in conjunction with another OR gives you OR square, contains edge between nodes that are reachable via two edges in OR. So you have two nodes that has been connected by means of edges, two edges. Again, if you consider OR power 2 in composition with the OR, that gives you the OR power 3 contains the edge between nodes that are reachable via three edges on OR, and that gives us a generic form of OR power n that contains the edge between nodes that are reachable via n edges in OR. So OR star contains the edge between nodes that are reachable via any number of edges via any path in OR. So you can just rephrase this contains all this OR star contains the edge between nodes A and B when A is a path of length at least 1 between A and B in R. So this is like an R star is a transitive closure of R. As you can see, A is connected to B and B is connected to C, C is connected to D. We can simply say that A and D are having some kind of relation. That's why it's called kind of transitive closure. Just for your example, let me tell you this connection here. Say you have these nodes. We know that this is say A, this is B, C, D, E, for our example F and G, right. So let's say that A is connected to B and B is connected to C. They have a relation C to D, D to E, E to F, F to G. So from here we can clearly establish the fact of transitivity. Since A is connected to B and B is connected to C, we are establishing the connection that A can be connected to C via B. So in connections with the connectivity relationship that we are talking about, that's where the actual degree of separation comes in. As you can clearly see from this connection A to G, there is 6 degree of separation, and this is what been explained here in this slide. Well, the definition of transitive closure is that there are edges between any nodes A, B that contains a path between them. Well, we talk about the edge, the path. Let's move on. How long are the paths in a transitive closure? With this, let's say R be a random relations on set A and A be a set with n elements, right? So consider a graph G with n nodes and some number of edges. Let's consider this. If there is a path of length at least 1 from A to B in R, then there is a path between A to B of length not exceeding n. Just to rephrase it again, we know that R be a relation on set A, so we know that A has n elements in it, and these n elements in set A. So let's we are converting this into a graph form. So from our previous lectures we know that we can in fact connect our terminologies of this mathematical modeling of relations into a graphical form. In fact, the graph relations where it has nodes and edges. So if you have a graph G with n nodes and some number of edges in it, and if there is a path of length at least 1, if we consider there is at least one path between A to B in relation with R, then there is a path between A to B of length not exceeding n. So let's consider the proof for this. Suppose there is a path from A to B in R, and let the length of the path be m, and let the path be the edges. We have x naught, x1, x1, x2, so on till x m minus 1 comma xm. So that is the path that you have, and that's the node x naught, x1, x2, x3. These are the nodes. If a node exists twice in our path, then it's not a shortest path. So we don't want to form a cycle coming back to the same node. So as we made no progress in our path between two occurrences of repeated nodes, so we can consider, if you like, you can graphically see how it works out. For example, let's talk about, so we have these nodes. So let's say x naught, x1, x2, x3, x4 until xm minus 1, xm. So just for our understanding, and here again in this path you can consider they are kind of connected. You can consider the connections in a different way. If you are, say this is connected to some other points here, and again the point is connected to this part. So anyway, this is kind of a graphical connections, and we can think about the path length in this preparation of transitive closure. So each node may exist at most once in the path. If you can make it possible that each node exists at least once in a path, that brings out many different questions. Is it the shortest path? Are we talking about any weights involved? When I say weights, it's like a cost involved in it. Well, we are not going to deep on that part in this transitive closure. We will talk about that when we come about the graph theory, in fact. Okay, let's see a proof by contradiction. Assume that there are n nodes in this path, and m is greater than n, m equals n plus 1, since m is greater than n. So by a pigeonhole principle, what is a pigeonhole principle? According to the pigeonhole principle, if there is a lot in which you have many holes where the pigeons can stay, and it leaves the hole and it comes back to this hole. If there is, say, 10 holes in it, and 10 pigeons can stay in this 10 holes, but what if there is another pigeon coming in? So you have 10 holes and there are 10 pigeons in the 10 holes, and you have the 11th pigeon coming in. What happens? Well, at this point of time, at least one hole should contain 2 pigeons. So that is the basic principle of pigeonhole. So there is n plus 1 nodes in the path, pigeons, and they have to fit into n nodes in the graph. Yes, they have to fit into the 10 holes, even if they had 11 pigeons. So thus there must be at least one pigeonhole that has at least 2 pigeons, as I just mentioned with that example. So there must be at least one node in the graph that has 2 occurrences in the node of the path. So not possible, as the path would not be the shortest. Well, in this case the path would not be the shortest, so it cannot be the case of n greater than n. So if there exists a path from A to B, then there is a path from A to B for at most the length n. Let's see this part here. Let MR be the 0, 1 matrix of relation R on a set with n elements. Then 0, 1 matrix of the transitive closure, you can see here m sub r star equals m sub r or m sub r power 2 or m sub r power 3 or the still m sub r power n. So here the nodes reachable with one application of a relation is considered as m sub r, and with the nodes reachable with 2 applications of relations is as if like having a 2 degree of separation there, and that's with nodes reachable with n applications of relations. So you can see that a real world problems can be even modeled as a mathematically using this matrix form. Well, this is kind of an open questions that you can work out. Try to find some examples in which you can really work on this 0-1 matrix form. Let's see some simple questions. Find a 0-1 matrix of a transitive closure with a relation R, say MR is given to you and the relationship is been established here. For example, 1 to 1 is 1 because there is a loop in 1 that goes back to 1. So 1 to 1 is 1, and there is a loop in 2 as well. So 2 to 2 is 2. So this is nothing but 1 1 is this one, 2 2 is this one, right? And 1 3, there is a path here, that is 1, and 3 to 1 there is a path, so this is 1. So in fact it's kind of an adjacency matrix. We call it as an adjacency matrix, and we talk about that in our graph theory part, but for your reference I just want to show that from this given graph this matrix has been formed. In fact we are modeling it. So here M R star equals M R or M R power 2 or M R power 3. So in fact because we just have 3 nodes here, we talked about n nodes in the previous slide. In this particular given graph we have only 3 nodes. So how do you find M R power 2? In fact we have to multiply M R times M R. So that's the basic multiplication problem here, and you get the results. So now you got the results. Why don't you try to draw a graph for this M R? This is nothing but M R power 2, and based on this matrix we are drawing this graph. Well, for your reference, for example, original matrix does not have a loop in 3, but the matrix here has a loop. For example, this is 3 comma 3 part, which has been expressed in this loop. Yeah, just for your reference, because I want to just emphasize this or M R power 2 is been expressed by means of this graph. Let's go further here down and find what is M R power 3. Again you multiply M R power 2 with M R, you get M R 3. Again for that you can come up with this matrix, and that's nothing but M R star. So for M R star you have to do OR process for all the given matrix. As you can see back, if you look back onto this question, this is the M R star, and for which you have to do the OR form of this whole thing. So let's do it here. So that's what is done here for M R star, and that's your proof there. In fact what we did or could have done is that compute the next matrix, that is M R power I, where I lies between 1 to n. So we were doing that. So do a Boolean join with a previously computed matrix. For example, like we did this part, if you recall what we did just now, and join that just like this, M R or M R power 2, and compute M R power 3. Yeah, we join and then we compute it. In fact join that with M R or M R power 2 from the above. So this is possible again. So the transitive closure algorithm is very simple, as we can see from this given pseudo code. We have A, B, and we have a for loop for 2 to n, and then we begin by multiplying A times M R, and then B you are ORing with A, and B is a 0-1 matrix for R star. So this simple algorithm is just for a transitive closure, and you do have a more efficient algorithm such as Warshaw algorithms. Anyway, we are not going to deep into that algorithms, just for your reference we are given here, so you can have a look at it. Yeah. So let's talk about some more information on the equivalence part of these relations. A certain combination of relations can be very useful. For example, we don't really consider many of these combinations in our course, but we will be considering some applications. Let's see, for example, a relation that with reflexive, symmetric and transitive can be established, and we are going to see about this partial ordering in few slides from now. For example, the equivalence relations. A relation on set A is called an equivalence relation if it is reflexive, symmetric and transitive. Okay, let's talk about what is this all about. Consider the relation R, and you have this A and B such that the length A equals length B. Okay, this is the given part. Now we are trying to find the equivalence relation with respect to reflexive, symmetric and transitive. Let's say, for example, where length A means the length of string A, and its reflexive would be length A equals length A. That is the property of reflexive. It is symmetric if length A equals length B, then length B equals length A. Yeah, that is a symmetric property. It is transitive if length A equals length B and length B equals length C, then length A equals length C. Yeah, that's R is equivalent relation that has been established by means of this three different property. And more on this equivalence relations, let's say A comma B such that we have M here. M is in fact is the module that has been established here for A minus B. So we call this concurrence module of M. It is reflexive if A comma A is the element of A, which means for all M such that A minus A. So A minus A is 0, which is divisible by M. So M divided by A minus A, that's given here, and it is symmetric if A comma B is element of R, then B comma A is an element of R as well. So A comma B means that here again you have say for example you have K times M equals A minus B. So you have the negating property here. B minus A is all equals minus K times M. So since we have the property of symmetric, so if A equals B, then B has to be equal to A. So it's like if A minus B, that should be equal to B minus A. So we have the property is that M such that you have B minus A, so B comma A should be in relation with R. Initially we said that A comma B is an element of R, then B comma A should be an element of R for the symmetric property. And for transitive, if A comma B is an element of R and B comma C is an element of R, then A comma C should be an element of R. So with that respect, we can see these three properties in which we have Km is A minus B, Lm is B minus C, and Nm is A minus C. So the property that we are trying to establish here is that finally A minus C, that is the property that we are trying to establish, and we have to prove this as well. Say for example, if you have Km plus Lm, that is A minus B plus B minus C, that reveals us K plus L times M equals A minus C. So this should be equal to the given part. So M divides A minus C, where N equals K plus 1. So the whole thing we talk about is the divisible by M from starting from the reflexive property in this equivalence relation. So thus this concurrence module M is an equivalence relation. We could conclude that. So if you recall this whole slide, it's one of the examples of equivalence relation, and we have these simple questions like, for example, which of these relations like 1 comma 0 comma 1 comma 3 is equivalence relation, determine the properties of equivalence relation that the others lack. So here you have this kind of ordered pairs in the set of 0, 0, 1, 1, 2, 2, 3, 3. So this has all the properties of the equivalence relation. Then you have another ordered pairs of 0, 0, 0, 2, 2, 0, 2, 2, 3, 2, 3, 3, 2, 3, 3. So this cannot be reflexive because 1, 1 is missing. Can you recall what are the properties? Like transitive property, for example, 0, 2 and 2, 3 are in relation, but 0, 3 is not in relation. So that connection of transitivity is missing. Again, consider this one ordered pair where you have the set in which 0, 0, 1, 1, 1, 2, 2, 1, 2, 2, 3, 3 is there, and again it has all the properties of equivalence relation. So if you want to really see it visually, in fact you can draw a graph using the nodes 0, 1, 2, 3 and try to put all the connections between them. In fact you can graphically see their relation. So given this D in the sample questions, we have 0, 0, 1, 1, 1, 3, 2, 2, 2, 3, 1, 3, 3, 2, 3, 3. So this properties is not transitive, as you can see 1, 3 and 2, 3 are in relation, whereas 1, 2 is missing here. So how about this set for E? Can you think about the properties? Yes, it's not symmetric because 1, 2 is present, but you don't have 2, 1. Yes, at this time of discussion in relations, you would be familiar with various statements that we made here during this whole lectures. For example, the last one in E, we don't have a transitive relation because 2, 0 and 1, 2, 0 and 0, 1 are in relation, but 2, 1 is not in relation. So by now you are very much familiar with this relational properties. So let's talk more about this with this example, sample questions you have. Suppose A is a non-empty set and F is a function that has A as its domain, and R be the relation on A consists of an ordered pairs x, y, where f of x equals f of y. So meaning that x and y are related if and only if f of x equals f of y. So we have to show that R is an equivalence relation on A. Remember, we are talking about these relations with respect to this particular set A that consists of the ordered pairs x, y. And if f of x equals f of y, that is what given to us, but for the property of reflexive, f of x should be equal to f of x for having the reflexive relation. Yes, this would be true as given same input, as a function always produces same output. And for symmetric, if f of x equals f of y, then f of y should be equal to f of x. That's the property of symmetric. And for transitive, if f of x equals f of y and f of y equals f of z, then f of x should be equal to f of z. Because it's a generic problem, so we have defining their properties, whether it's reflexive, symmetric or transitive by these definitions. Again, we have to show that a relation R consists of all pairs x, y, where x and y are bit strings of length 3 or more that agrees except perhaps in their first 3 bit is an equivalence relation on the set of all bit string. Say for example that f of x equals bit string formed by last n minus 3 bits string x, where n is the length of the string. So we have to show that let R be the relation on A consists of the ordered pair x, y, where f of x equals f of y. So this just we have shown this in the previous slides. So you can have a look at this and try to establish a proof for this question. What do you think? Well, this is a generic question again. We don't have a specific details, but only details that is given to us is that x and y are bit strings of length 3 or more. and that agrees to perhaps in the first 3 bits. If you can take they have as if they have 3 bits of information. When coming to equivalence class, suppose you have a relation R be an equivalence relation on set A. The set of all elements that are related to an element A of A is called the equivalence class of A. Remember here A, the small a, is an element of the set capital A. So set of all elements that are related to an element A in the set A is called the equivalence class. So equivalence class of A with respect to R is denoted by A sub R. So when only one relation is under consideration, the subscript is often deleted. So when you have just only one relation. Note that these classes are a kind of disjoint class. So as the equivalence relations is a kind of symmetric relations that establishes this. So just few points on the equivalence class. If you consider this relation R for the set A comma B such that A mod 2 equals B mod 2, thus all even numbers are related to each other, as are all odd numbers. So even numbers forms the equivalence class, so do the odd numbers. Say for example here the equivalence class for even numbers is denoted by 2 or 4 or 8 or any even number like 7, 8, 4, etc. And for 2 again you might consider, if you are considering the negative and positive integers, you have -4, -2, 0, 2 and 4, so on. So it's kind of a 2 is the representative class for equivalence class, because this equivalence class is about the all even numbers that are related. So 2 should be the representative of the equivalence class. So there is only 2 equivalence class formed by means of this relation here. And if you consider this part here on this equivalence class, so the relation R which has the set A comma B or the elements, they are related such that A equals B or B equals minus or A equals minus B. So we say that every number is related to additive inverse. Because of minus we refer that. So the equivalence class of an integer A, so A, that is for example it can be 7 equals 7 comma minus 7, and 0 we do not have any negative part, so A is just A comma minus A. So any value that has been given here, it has to be of this form. So looking at these 2 examples of equivalence classes, you could clearly see that there are infinite number of equivalence class found by the equivalence relation, whether it's about even numbers or about odd numbers, or here in this example we just have A equals B or A equals minus B, that is with respect to the integers. Well, today we talked more about some of the applications of relations, respectively we saw some of the unique features of relations, and there are more applications of relations yet to be discussed in our lecture. So I am looking forward to see you in the next lecture where we discuss more on this applications of relations. So until then, have a good time and see you in the next class. Goodbye.